our electric machine is the transformer. Okay, so the outlines of this part are overview, transformer construction, review of Faraday's law and the induction, ideal transformer, and the last element in this part is the real transformer. So overview, a transformer is a static electromagnetic machine. So the transformer is an electric machine. We said that the electric machines that are devices that transform the form of energy from electrical to mechanical or from mechanical to electrical. But the transformer is a static machine. We don't have motion. We don't have rotation. So this static electric machine transforms the electric energy from electric form to electric form with different amounts of voltage and currents. So a transformer is the static electromagnetic machine. It has no moving parts. We don't have a rotor. Use it commonly to change the level of AC voltages and currents. Okay, different types of the transformer. We have, of course, a different type of transformers. So, different type of the transformer. The transformers we care a lot, of course, are the power transformer of distribution and transmission. So I show you before in our first session a picture like this, which is different phases how the electric energy transmitted from the generation to the consumers. So here we see a power plant where the generation done. So at the output of generator, we have to raise the level of the voltage. And I told you before, this is for economical reasons. When we raise the level of the voltage using those, we call them transmission transformer. When we raise the level of voltage, the current get decreased. And when we decrease the current, the cross section of the cables that use it for transmitting the energy get reduced also. So this is for an economical reasons. So then the electric energy transferred through those transmission lines. Then from transmission lines we have a transmission transformers. You're seeing them here in the figure. After the transmission transformers, those are used here, for example, to interconnect different networks with each other. So you may find transmission transformers not in the power plant, but we call them substations here. We call them substations. Those stars here. Those substations are used to connect the networks between each other. After the transmission transformers, we have a distribution transformers. So those to reduce again the level of the voltage. You see this example. The level of the voltage here is between 200 kilovolt and 1 megavolt, and the level of the current here of the voltage is between 15 and 25 kilovolt. This is the example. Of course, it's not for our countries. We may, here in Algeria, we may find different levels of the voltage and the currents. After that, we will have service transformers that transfer the electric energy to the consumers. And the figure below conclude this cycle. This is an example of the US, of course, AC generator. The level of the voltage here, 30 kilovolts. So the transmission transformer will raise this voltage until 500 kilovolt. Then the distribution transformer, they have different levels. So the first one will reduce the level of the voltage from 5 kilovolts to 44 kilovolts, then 4.6 kilovolts, then to 120 volts, which is the service electricity that use it in houses and cities. Okay, so this is an example of the US power generation, transmission, and distribution. And this just to show you the importance of the transformers in the AC network. So we cannot make an AC network without transformers. Okay, let's move to the next slide. So this was the first different type of transformer, which is power and distribution transformer. The second type of the transformer, let's use a different color. The second type is isolation transformer. So this isolation transformer, we may find it in some electric installation. Isolation transformer are used to electrically isolate electric circuits from each other and eliminate electromagnetic noise in many types of the circuit. So this type of transformers does not increase or decrease the level of the electric energy. So its input, the voltage of the input equals to the voltage of the output. Also, the current of the input is equal to the current of the output. These transformers are placed in such electric installation just to provide a physical isolation between two circuits in order to eliminate such noise, or can be used also for a protection purpose. In such electric circuits or in electric installation, we use those transformers. They don't increase or decrease the level of the voltage of the current. The input is equal. Their inputs is equal to the output, but they use it to provide that physical separation between the circuit elements. And the last type here is the instrument transformer. So those transformers are used for measurement purpose. We may find a potential transformer like the one shown here, and these also use it in the networks because we cannot measure the high voltage directly. So we use those potential transformer. And also we call this a current transformer. The instrument transformer are used to measure high voltage and the current with the standard small range. So those transformers of the current or the voltage use it to measure the high and the high voltage and the high current. So those devices give us they have what we call it a coefficient or a factor indicate to a higher voltage. They may divide the voltage over 1000, for example, or just they have a ratio of a report to give us to indicate the real voltage value. So those are the types of the transformer. Firstly, the power and distribution transformer. The second one is the isolation transformer, and the third one is the instrument transformer. Now let's see the construction of the transformer. Of course, the transformer is a magnetic, has a magnetic circuit. A transformer is essentially consisted of two or more windings coupled by mutual magnetic field. Mutual, which means مشترك بيناتهم, mutual. It's between them. So the flux here in the core is the flux of both coils or windings. Okay. So the transformer essentially consists of two or more windings. More maybe in the three-phase. There is also three-phase transformer, but here we are going to focus on the single-phase transformer coupled by a mutual magnetic field. So the magnetic core is made up of stacks of lamination. So lamination, which means sheets, thin sheets, like as you see here in this figure. Those are the sheets compacted with each other to consist the core. So this is a single lamination, and we know why we use those lamination in order to reduce the eddy currents in the core. So this is the construction of the transformer. It is constructed by a core made from lamination from silicon steel. The material here is silicon steel to reduce the core losses exactly, which are eddy currents. And we have two windings. The first winding we call it primary winding, and the second one we call it secondary winding. So the winding of the transformer that's connected to the AC supply, the winding that's connected to the source called primary winding, and the winding connected to the load called secondary winding. So we can call them primary winding, and we can primary winding and the secondary winding, and we can call them with other nomination. The winding with higher number of turns, the winding with higher number of turns called a high voltage winding, HV, and the winding with lower number of turns called low voltage winding. So here the high voltage winding can be primary and can be secondary. Also the low voltage winding, it can be primary and can be secondary, because we have a step up and step down transformer. The transformer that rise the level of the voltage and reduce the level of the current, and the transformer that reduce the level of the voltage and rise the level of the current. And the same transformer can be used for both purposes. If we choose the first one, the high voltage as primary, it's depend if we choose which winding is the high voltage or the low voltage. Let's move to the next slide. So we are also with the construction. In the construction, we may found two different types of construction. This is the simple one, which called a core type, as you have seen in the previous slide. This construction called a core type transformer. Okay, just a minute to add some of your colleagues. Okay, so we call this a core type transformer according to the shape of this core, and we see this is the primary winding and this is the secondary winding. Okay, so here you are seeing a cross section of the transformer. This is the primary winding and this is the secondary winding. We call this a core type, and you see here the sheets of the core types, how they are made. Also, we have the shell type. This is the shell type, which is the most used, actually. The shell type, we can note here that the windings are above each other. The primary and the secondary are above each other. They concentrated in the middle of the core, and they are above each other. So this type can reduce a lot the leakage flux. Okay, so this shell type, which is the most used, actually, is used in order to reduce the leakage flux. And those are the type of the lamination in the shape of E. So the lamination sheets of this shell type are in the shape of E. And those are the lamination of this shell type. In the shell type transformer, the low voltage winding is placed closer to the core. So the one here inside, okay, let's use the pen. The one here inside is the low voltage, winding, and the one in the top is the high voltage. Let's change the color. The one here, this one is the high voltage currents, and this I guess for the purpose of cooling of the transformer, because the low voltage winding has of course its high current, and the cross section of this winding is bigger than the high voltage winding. So this design simplifies the problem of insulating the high voltage winding from the core and reduce the leakage flux. So this shell type proposed to reduce the leakage flux, and actually all the transformers exist are shell type transformers, but in our studies always we consider the transformer as a core type in order to simplify, but all transformers exist today are a shell type in the shell type construction. Just a minute. Okay. Let's move to the next slide. So,
sir, please.
Yes.
Can you go back to the slide? Sir, what about here in the core type? Where is the secondary and the primary? Is it the same like in the primary is in the left and secondary in the right?
You are not obliged. We can choose as this one is primary and this one is secondary. It's our choice. Okay. Always
so the primary, in the core type we can choose.
The primary is the one connected to the source, and the secondary is the one connected to the load. Okay. Whatever we choose, which one connected to the source and which one connected to the load. Okay. Okay. The next slide, element number 3 is the review of Faraday's law of induction. We have seen this, of course, in the magnetic circuit, maybe one of the last elements in the chapter. Faraday's law of induction. The induced voltage can be found. So, before we are talking about how we can produce a magnetic field or how we can have a flux. And one of the cases is when we have a time change a flux So this is why the transformer work only with AC, because transformers are based on Faraday's law. So if this voltage is DC, if we give a DC voltage to the transformer, the flux will be constant and this derivative will be 0. That's why the transformers work only with AC. Okay. So according to the expression number 1, so in this chapter I have added the numbering of the expressions. N, of course, is the number of turns. Phi is the flux passes through the coil. So when we calculate the derivative of this expression, you have seen it before, we get this expression in terms of RMS voltage equals to 4.44, and 4.44 is 2 pi over square root of 2. This is 4.44 times N times phi max times F, which is the frequency. And if the voltage, so this is an EMF and this is a voltage, so the difference between them, we are going to see it inshallah in between the difference between real and ideal transformer. But if we consider that the voltage drop due to the resistance, because the winding of the transformer has a resistance. Okay, so the voltage equals to the EMF plus that voltage drop, which is Ri. But here, if we neglect that voltage drop, the EMF will be equal to the voltage. Okay, So if the voltage drop due to the resistance of the winding is neglected, the EMF equals to the applied voltage. So V equals to 4.44 times N times phi max times F. And of course the flux equals to F over 4.44 times F times N, which is the number of turns. So why we are seeing this expression? This is the principle of operation of the transformer. Okay. Why? When the flux that's produced by the primary winding go to the secondary winding, it will create another voltage, which is the secondary voltage according to this expression. Okay, so this is how the flux creates another voltage. You asked me before how we can get we get induced voltage using induced voltage using a time changing flux, and you ask me where did get that flux. Here we have flux. Where this flux came from another source, came from the second primary winding. So the flux of the primary, when travel, let's say travel to the secondary, it will create another voltage according to this expression. So this is the output voltage, can be calculated according to Faraday's law. Number 4, ideal transformer. So firstly, to simplify the study, let's consider our transformer as an ideal transformer. Then we are going to see the real transformer. So of course our focus is on the real transformer, but here, to simplify study, let's start with the ideal transformer to understand such things. Then when we pass to the real transformer, things will not seem complicated. So consider the transformer with two winding primary of N1 turn and secondary winding of N2 turns, as shown in the figure number 6 here. Let's consider an ideal transformer. What does it mean, an ideal transformer? Firstly, the winding resistance are neglected. The resistances, the internal resistances of those winding, the primary and the secondary, are neglected. So the resistance is 0. There is no leakage flux. Okay, there is no leakage flux. The core losses are neglected also. There is no core losses. The permeability of the core material is almost infinite. So the exciting current required to establish flux in the core is neglected. What does it mean, this passage? If the permeability of the core is infinite, we will not have a reluctance. We know that the reluctance equals to what? Equals to L over mu times A. So if this is infinite, the reluctance is equal to 0. So we don't have a reluctance in this ideal transformer because the permeability of the core has an infinite value. Okay. And also the magnetic core material don't saturate. So you have seen before the magnetizing curve. So the saturation point here, it's not considered. So those material does not saturate. And this, we call these assumptions, Faradayat. They are not real. In reality, we don't have this. Maybe in such cases, if we use specific materials, but in general, we don't have those. There is no material that does not saturate, or material without resistance, or whatever it is. It small. Okay, so those are assumptions. Faradayat. Okay, in order to simplify our studies before passing to the real transformer. So those are assumptions, so you should save them in your mind when we have an ideal transformer. Okay, so when the primary winding is connected to the AC voltage source V1, when we have a voltage here, a voltage source here in the primary, a flux is established. So the voltage of the source will establish or create a flux in the core. Okay. Okay. So the voltage of the source, it will create a flux in the core. Then this flux, okay, a flux phi will induce a voltage in the secondary. This is the principle of operation of the transformer. So the primary and the secondary are not connected physically. There is no wire, for example, between the primary and the secondary. That's why we use transformers for isolation. They are isolated. Only the flux which transfer from the primary to the secondary. The voltage of the source creates flux here. Of course, here in the ideal transformer, we are neglected the leakage flux. So this flux, the linkage flux, that's created in the core, when it travels to the secondary, it will induce another voltage, which is called a secondary voltage. So this is the voltage expression of the primary voltage, number 5. A flux phi is established in the core and the voltage V2 will be induced in the winding. The secondary winding induced voltage is given by this expression. Yes? Okay. So this is the principle of operation of the transformer. I will repeat. The voltage of the source will create a flux in the core. Then this flux, when it transferred to the secondary, it will create another voltage. So here, the difference, because here we have the same flux, of course, it's the same flux that transferred from the primary to the secondary. But the difference of the amount of the voltage of the primary and the secondary depends on the number of terms. So V1 equals to E1 equals to N1 d phi over dt. V2 equals to E2 equals to N2 times d phi over dt. The same flux, but the number of terms is different. So the voltage is different. Okay, let's move to the next slide. So from 5 and 6, we can write in this expression. So if we divide those expressions part by part, okay, so let's go to the table. Okay. Okay, so here from 5 and 6 we have V1 over V2 equals to E1 over E2, and this equals to N1 over N2 from those expressions 5 and 6. V1 over V2 equals to E1 over E2 equals to N1 over N2. So here in number 8 are written in terms of RMS. So here the small letters are instantaneous values and the capital letter are RMS. Okay, no problem. So let's work with RMS's values. So this report, we call it a turns ratio, A. This is A, which is the turns ratio. V1, A equals to what? Equals to V1 over V2, and it's equal to E1 over E2, and it's equal also to N1 over N2. So we care about this. So exactly, then the turn ratio is equals to N1 over N2. So where A is called turns ratio. So if the number of turns of the secondary winding N2 more than N1, if the number of turns in the secondary winding is more than the number of the turn of the primary N2 greater more than N1, the transformer is known as a step up. What does it mean, step up? It means that this transformer rise or increase the voltage. Okay. So let's draw a row here. So step up, which means that this transformer increase the voltage. If the number of turns of the secondary winding is more than the number of turns of the primary winding, we call this a step up transformer. Elevator, we can call it elevator, because it increases the level of the voltage. In the same time, it decreases the level of the current. We are going to see it later. If the number of turns of the primary winding is more, if the primary is more, so N2 less than N1, this transformer called step down. Okay, step down, which decrease the level of the voltage. So using the expression shown in 8, let's in order to prove this, why when N2 greater than N1 we call it step up, and when N2 less than N1 we call it step down. So using this expression, let's go to the table. Using this expression, of course, we have V1 over V2 equals to N1 over N2, and this equal to A. And this means what? So let's take this equality. This means that that V1 equals to what? Equals to V2 times N1 over N2. Okay. And equals to what? V1 equals to V2 times A. So if N1 is bigger than N2, it means that A is more than 1. Okay, because it's a ratio. Okay, just please focus on this. You may see it complicated, but it's not. Okay, sorry. So if N1 is bigger than N2, okay. If N1 is bigger than N2, so which means that this transformer is step down transformer. Okay, as we have seen said here, if the number of turns primary is more, okay. Sorry. So if the N1 bigger than N2, A more than 1, which means that V1 is more than V2, because here V2 راهو مضروب في amount more than 1. Okay. Have you get it or not? Or should I repeat it? Because this is the main objective why we study the ideal transformer, to explain the meaning of the terms ratio. Okay, so we said that V1 over V2 equals to N1 over N2 equals to A. Let's change the color. Equals to A. And we said that if N1 more than N2, the transformer is step up. Those are the conditions. If N1 less than N2, this transformer step down. So let's write it like the step down and step up. Okay. So if N1 is more than N2, this equals to what? It can be written like this. Equals to V1 equals to A times V2. So if N1 more than N2, this ratio A is more than 1. And of course, according to this equality, V1 is greater than V2, and this transformer, so V2 is less than V1, so this transformer is step down transformer. But if N1 is less than N2, this becomes less than 1. It's between 0 and 1. So here, V1 equals to A times V2, and A is less than 1, which means that V2 is greater than V1. And this transformer is step up transformer, a step down transformer. Okay. Okay. Have you get it, or should I repeat it before moving to the next element? Yes. Yes.
Can you repeat it, please, sir? I had a
Okay.
problem.
I know that you have such ambiguity concerning it. I know. This is the objective of studying the ideal transformer, because if it was real, we will have voltage drops. So this will not be exact. Okay, that N1 over N2 equals exactly to V1 over V2, because we have voltage drops. But in the ideal transformer, since we don't have voltage drops, we study the erase. Why we cannot erase those? Okay. So let's use the pen here. Okay. So starting from this, V1 equals to V2. V1 over V2 equals to E1 over E2 equals to N1 over N2, and we call this a turn ratio A. So if the number of turns secondary winding is more than the number of turns of primary winding, so the first case, if N2 is more than N1, N2 more than N1, which means A less than 1, A between 0 and 1. Okay, this is the first case. The transformer is a step up. Why it's step up? Let's take this. Okay, from this we can get this. Easily we can get this. So here V1 equals to what? Equals to A V2. A is less than 1. So according to this, V2 is greater than V1. V2 راهو كبر من V1 because V2 is مضروب في coefficient less than 1 باش ولا equals to V1. Okay. هنايا we reduce V2. We يعني okay. We can write it like this. V1 over A equals to V2. And you know, كي نقسم على حاجة less than 1, the result will be bigger, more, ولا لا? Okay. Yes or no? Yes?
Yes. Yes.
Okay. So this is the first case. If n2 more than n1, which means that A, the turns ratio is between 0 and 1, V1 equals to A V2, or we can say that V1 over A equals to V2. So here the voltage, the output voltage. Of course, V1 is the input, which is the primary, and V2 is the output, which is the secondary. V1 over A, which A here is less than 1. It's between 0 and 1. V1 over A equals to V2. So the output is more or greater than the input. The second case, when n2 less than n1. So if n2 less than n1, so A is more than 1. 1.234, we don't know. Okay. Or maybe you can assume it. You can replace A by any value, and you will get it. Okay. So if A more than 1, V1 equals to what? V1 over A, it's the same like this, equals to V2. So if we divide V1 over a value more than 1, the result will be less than V1. Okay. I think we should have an example to understand it. Okay. Okay. Let's take the simplest example we can take. Okay. Let's, for example, consider that n1 is 1000 and n2, the first case, n2 is 2000, for example, or okay. معلش خلي. Let's take n1 500 and n2 take n1 500 and n2 1000. Okay. So here n1 n2 is greater than n1. It's a step up. Okay. A equals to what here? A equals to 0.5. Okay. So according to this expression, V1 equals to 0.5 V2, or V1 over 0.5 V2. So if V1, let's give it a value. If V1, for example, if V1 is 220, V2 becomes what? V2 becomes 440 volt. Okay, V2. This is the first case of step up. Is it clear?
Yes, sir.
Yes.
Okay. Okay, alhamdulillah. The second, let's manage the second one. Let's switch now. Let's consider that V1 is 1000 and N1 is 1000. N1 is 1000 and N2 is 500. Here A is equals to what? Equals to 2. 10 over 5 is 2. Okay, so according to this expression, number 9, V1 over A equals to V2. So if we consider that V1 is 220, 220 over 2 is 110 volt. So this one is step down transformer, which decrease the voltage. The first one rise, the second one decrease. I hope you can save this in your mind. And if you feel it complicated, just give example as we have done now, and you will get it. If N1, we said before, at the beginning we said the winding with more number of turns, we call it high voltage. So here, since N has the bigger number of turns, and here high voltage. Here N2, he has less number of turns. She has here low voltage. Okay. Wherever you find the bigger number of turns, that's the high voltage winding. Wherever you have the less number of turns, that is the low voltage winding. In the first case, the step up transformer, N1 is the low voltage. The primary here is the low voltage, and the secondary is the high voltage, because N1 less than N2. In the second case, in the step down, N1 is the high voltage winding, because it has because N1 bigger than N2, and N2 is the low voltage winding. So that's why we have primary, secondary, but each one of these, primary can be high voltage or can be low voltage, and the secondary can be high voltage and can be secondary voltage according to the number of turns. So this is concerning the number, the ratio, the turns ratio, and why we study the turn ratio in case of ideal transformer, to avoid those voltage drops. Okay, so here if we have only V1 and V2, we neglect those voltage drops of R1 and R2 and okay. Now let's move to the next point. Since the core of an ideal transformer is infinitely permeable, yani the permeability is infinity. The net MMF is 0 because the reluctance is 0. The net MMF is 0. This is like Kirchhoff's law. When we have a mesh, the voltages in this mesh equals to 0, of course, because the reluctance here is 0. So using this expression, so now let's see the relationship between the turn ratio and the current. We have seen the relationship between the turn ratio and the voltage. Let's now see the relationship between the turn ratio and the current. So using this expression, the net MMF of the transformer equals to 0. Sorry, here should be N2 and I2. Sorry. Okay. Because the reluctance is 0, the permeability is infinite. Using this expression, okay, the mistake here also, I should correct it. From 10, we have N1 times I1 equals to N2 times I2. Then according to this expression, I1 over I2 equals to what? Equals to N2 over N1. So here it's vice versa with voltage. Okay, we have written on the table before, we have written N1 over N2 equals to E1 over E2, sorry, E1 over E2 equals to V1 over V2, but it's equals to I2 over I1. Okay, so it's vice versa between voltage and the current, the relationship with the turn ratio. Okay, so using the expression of the MMF, N1 times I1 equals to N2 times N2, then I1 over I2 equals to N2 over N1 and equals to 1 over A. This one is the 1 over A. So the relationship between the turns ratio, the relationship of the turn ratio with voltage and the current is opposite. Okay, that's why when we said step-up transformer, it increases the voltage, but in the same time it decreases the current. Also, the step-down transformer, it decreases the voltage but increases the current. You know that the transformer does not change the power. The power S, for example, of the primary equals to S of the secondary, the apparent power. But so which means that V1 times I1 equals to V2 times I2. Of course, with losses here in ideal case. Okay. So the power does not change. They change the voltage and the current, but this product stay the same. Okay. So the current, when it step up, always we talk about voltage. It step up, it increase voltage, but in the same time it decrease the current. The same thing with the step down. It decrease the voltage and in the same time increase the current. Here we have an example. We have an example. Okay, is it clear here with the current before seeing the example? Yes?
Yes.
Okay, so it's the vice versa. As the expression we have written here in the table. Okay. So N1 over N2, which is A, equals to E1 over E2 equals to V1 over V2, but it's equals to I2 over I1. So it's opposite with the current. That's why we said that the operation of the transformer, okay, when it increases the voltage, it decreases the current, and when it decreases the voltage, it increases the current. Okay, let's see this example. It's a simple one. Okay. The eraser, where is the eraser? Okay. Okay. Determine the number of turns of the primary and the secondary winding of 60 Hertz, 240 and 120 ideal transformer. So when we write like this, so this is the high voltage and this is the low voltage. If the flux in the magnetic core is no more than 5 milliweber. Okay. So using the expression of what we said when we explained the principle of operation of the transformer. So if this is the core, we said that the voltage of the primary will create a flux here. Then this flux will create a voltage in the secondary. So using Faraday's law, the expression of the voltage V1 equals to what? Equals to 444 times N times F times phi max. So here we have N1, we have the frequency. Frequency, of course, is the same. The transformer always keep the same frequency and almost the same power, if we not consider the losses, okay, and phi max. So using this expression, N1 equals to what? Equals to V1 over 4.44 F times phi max, and this equals to what? Okay, this equals to what? This equals 240 over 4.44 times 60 times 5 to the power minus 3, because it's milliweber, and the number of turns is 180. Okay, 180. Now this is the number of turns of the primary. Okay, we have found it using Faraday's law. So now how we can find the secondary? Of course, using the expression of the turn ratio, we have N1 over N2 equals to V1 over V2. We have V1 and we have V2, of course. V1 is 240 over 120, which is equals to 2. Be careful, this expression is for the ideal transformer, not for the real transformer. Okay, it can be valuable for the real transformer in one case, when in the no load case. If the transformer is not connected, the real transformer, if it's not connected to the load, there is no resistance, the current is almost zero. So this expression can be valuable in one case, when we don't have load in the real transformer. But this expression exactly for the ideal transformer. So N1 over N2 equals to 2, which means that N2 equals to N1 over 2. And it's 990 turns. Yes?
Sir, I have a question concerning this exercise. Concerning N2, can we use the same expression?
Then we use the same expression
for to calculate N1. Yes.
The same expression. I didn't try it, but yes, we will. The flux is the same. The frequency is the same. We are going to replace 240 with 120. Okay, so yes, it's the half. Yeah. Yes, it's the half. Okay, so I should stop here. قريت بزاف اليوم. Okay, we done almost 1 hour. Okay, I should stop here. We still have impedance transfer, one element. Then we pass to the real transformer. Okay.